Okay. All right. This is CS50. One sec. Sorry. Can we do that again? And this is week 5, which is going to be our last week in C. But what that means is that we'll have, okay. But with this week, with last week, and really all of the weeks prior, have you been hopefully acquiring, if slowly and with some challenge, like some fundamental building blocks that are still going to underlie everything we continue doing in the semester, even as we transition to so-called higher level languages. Next week, indeed, we'll introduce Python, a very popular language that does not have pointers, does not have memory management at this very low level, but that's really just because someone else wrote the code that will do that for you, and it's going to make our lives easier because it means when you want to solve a problem conceptually up here to just get real work done or build something amazing, you don't have to really get into the same weeds as we have been deliberately this week and now last. But the goal ultimately is that you better understand and can better harness then all that a computer can do, even in those higher level languages. So today we're going to focus particularly on data structures, how you might structure your data in memory, which really amounts to building things digitally, stitching together ideas and concepts in memory using this new building block from last week, which of course are these pointers. Pointers allow you to store addresses in memory, like in variables. But with those simple addresses, we can sort of leave these breadcrumbs. We can point from here to there, and we can conceptually stitch pieces of data together. But there's going to be different ways of doing that. And in fact, today we'll first focus on what's technically called abstract data structures. And we've seen abstraction before, sort of a simplification at a higher level of some lower level, more complicated ideas. But an abstract data structure is really one that can be implemented underneath the hood in code in any number of ways. What's important in an abstract data structure is just what it can do for you and what features or properties it has. So for instance, in the world of computer science, a queue is actually a technical term. This is a type of data structure that we could theoretically build in code in C or really any other language. But a queue has properties just like queues in the real world. For instance, if you've ever lined up for something to get food in a restaurant or go into a store or wait for the airport to clear you, well, you've lined up in a queue being some sort of line. But what's noteworthy about queues are specific properties. They are first in, first out data structures, either virtually or in the human world, which is to say the first person in the line should ideally be served first at the restaurant, or the first person in the line should get through airport security first. By contrast, if it weren't first in, first out, you can imagine how frustrated you would be if you have this sort of inherent unfairness. In fact, if you've ever been in line at a store, a supermarket, or the like, and all of a sudden they maybe open a new line, and now the person behind you gets to kind of cut ahead and go forward, that's because they've broken the concept of the cube. So it has this inherent potential for unfairness unless you maintain this first in, first out property. This would be true too for like a to-do list, just for productivity's sake. If you're in the habit on paper or virtually making a to-do list, ideally, you probably want to go through that list top to bottom so that you actually get the first stuff you thought of done first, rather than always focusing on your most recent thought. Now, within the world of queues, there's generally two operations, two functions, if you will, that any queue would have, either in the real world or in the virtual. Enqueue is usually the technical term to mean adding something to a queue. But specifically, it means adding it to the end of the queue so that someone isn't cutting in line, for instance, to go up front. And then dequeue is just the opposite. When it's time for the first person in line to be served, the time for the first person in line to go through security, they are dequeued, so to speak. So a technical concept ultimately as it's implemented in code, but it's really just a real world concept. And these are in contrast to another abstract data type that we might call a stack. And a stack, much like a stack of trays in the cafeteria, has sort of fundamentally different properties. You can still add and remove things from them, but consider what happens. Whenever they clean all of the trays in the cafeteria or the dining hall, they put one of the trays down here, and then the next one on top of it, and then the next one on top of it, and so forth. But of course, which tray do you presumably take as a user of that physical stack? the top one, presumably, right? Like you're not going to futz down here and try to pull one out. And so that would seem to have an opposite property, LIFO. Last in, first out is what characterizes something like a stack. And that just makes sense, certainly in the physical world, of stacking all of those cafeteria trays, because it just makes more sense to grab the most recently added one, the last added one, first. And at least in that context, the trays don't necessarily care what order they're used in. But even then, you could imagine that maybe there's some old, dirty, nasty tray at the very bottom that like never gets used because you're constantly replenishing the stack. So there might very well be side effects of these kinds of features. You might be familiar with using Gmail, for instance, or really any email program. What you're looking at in your inbox is technically a stack, at least if you've left the defaults configured. Why? You get a new email. Where does it end up? Not like 5 pages of emails later, presumably right at the top. And the next one's right at the top, right at the top, right at the top. And so if you're like me, you're guilty of eventually losing track of some emails. Why? Because you've pushed so many more emails onto the stack that you sort of lose track of the things you got earliest. Last in, first out, though, is maintained. The most recent email you get might very well be the first one you reply to, but that's not necessarily good for responsiveness to everyone else out there. Similarly, if you store like all of your sweaters in a stack like this, like a pile of black ones below which is a red and then a blue, stack might be perfectly fine for keeping things organized. It's sort of the sane way to do it if you just have a shelf in your dorm room or home. But what's going to be a side effect of using a stack to store your sweaters if they're these in this way, as opposed to a queue? Yeah? It's harder to get the red and blue ones. So presumably, you're going to much more often wear, for instance, if you will, black instead there. Now, the operations for adding things to a stack are similar in spirit, but just different vocabulary. You push something on top of a stack. Even though it's more like in the tray world, you sort of place it or rest it. But pushing means adding something to the top of the stack, and popping means removing something also from the top of the stack. So it's not a matter of enqueuing at the end and dequeuing at the beginning. With a stack, everything's happening on top. You're pushing onto the top and then popping off of the top. Now, when it comes to actual code, how might we implement something like this? Well, let's just focus on really how you might implement the data structure itself, and we won't implement any functions. You might implement the notion of a stack like this. We've seen typedef before. It just means define a new type of my own. Struct means here comes a structure, aka a data structure of one or more variables within. And let's suppose, like last time we defined already like a person data type using a separate typedef, and every person has like a name and a number or whatever. Let me just stipulate that person exists already. So here you might have, to implement a stack, an array called people of some capacity. Maybe it's an array of size 10 or 100 or whatever. This is a constant here in this context, capacity. And every element in that array is a person structure. And I now have this too, size. Now this almost seems like a synonym for capacity, but maybe intuitively, anyone want to propose why I'm apparently maintaining separately the capacity of the stack, but also the size of the stack? Why these two distinctions here? Yeah. Yeah. Perfect. The capacity is how high the stack could be, like how much room is there for those sweatshirts in my closet, for instance, whereas size is just literally at this moment in time how many sweatshirts are in the stack. It's either capacity or fewer, presumably, in total there. So what is capacity? Well, we could implement this in, perhaps a familiar way. I might just define a const somewhere else in my code of type int that just defines it to be capacity 50. But what perhaps is going to be the downside of implementing a stack in this way, of using an array inside here? Like, what's a downside now of implementing a stack using an array and this size variable within? What's a caveat here, perhaps? Any hands? Yeah. OK, so it's going to be harder to reach elements that aren't the last one. That is the most recently added one. So there could be some sweatshirts, so to speak, way down below. So we've seen that before, too. But at some point, too, a limitation of this design is is what it's going to be finite, right? I can maximally fit in this example 50 sweatshirts or 50 emails or 50 cafeteria trays, which is fine, but at least it's indeed finite. And at least in the computer's memory, it might be nice to use more and more and more, maybe as more things are getting added to the computer. So maybe I make this 500, or heck, why don't I make it 5,000 or 50,000? Well, what's the trade-off there? If I want to have enough room to grow, it seems like I should just crank up the value of capacity endlessly. But why might I not want to change the 50 to 500 or 5,000 or 50,000? What's the trade-off there, perhaps, just intuitively? Yeah? OK, you don't want to touch memory that you're not supposed to be touching. And in this case, that wouldn't be a risk per se unless you indeed overflow the stack. But there's a related issue in asking for that much memory. What would another downside be? Yeah, OK, exactly. So if you've got a capacity of 5,000, but you're only using one of those elements, it's awkward, to say it non-technically, which is just to say very, very wasteful, right? That's just bad design. It's correct. It will work for up to 5,000 elements. But my gosh, you're wasting 4,999 extra spots. And that's not going to end well, especially if you're using more data structures in memory, like your Mac, your PC, your phone is surely going to run out of memory if you ask for that much. So it'd be nice if there was a bit more dynamism there, whether it's a stack or a queue, both of which might be implemented a little similarly in spirit. But let's conclude this abstraction by comparing, thanks to a friend of ours, Professor Shannon Duvall of Elon University, who kindly put together this graphical animation that's just under 2 minutes long that paints a picture of these two types of abstract data structures. And then we'll dive in underneath to how we might implement problems like these. If we could dim the lights dramatically.
Once upon a time, there was a guy named Jack. When it came to making friends, Jack did not have the knack. So Jack went to talk to the most popular guy he knew. He went up to Lou and asked, "What do I do?" Lou saw that his friend was really distressed. "Well," Lou began, "just look how you're dressed. Don't you have any clothes with a different look?" "Yes," said Jack, "I sure do. Come to my house and I'll show them to you." So they went off to Jack's, and Jack showed Lou the box, where he kept all his shirts and his pants and his socks. Lou said, "I see you have all your clothes in a pile. Why don't you wear some others once in a while?" Jack said, "Well, when I remove clothes and socks, I wash them and put them away in the box. Then comes the next morning, and up I hop. I go to the box and get my clothes off the top." Lou quickly realized the problem with Jack. He kept clothes, CDs, and books in a stack. When he reached for something to read or to wear, he chose the top book or underwear. Then when he was done, he would put it right back. Back it would go on top of the stack. "I know the solution," said a triumphant Lou. "You need to learn to start using a queue." Lou took Jack's clothes and hung them in a closet, and when he had emptied the box, he just tossed it. Then he said, "Now Jack, at the end of the day, put your clothes on the left when you put them away. Then tomorrow morning when you see the sun shine, get your clothes from the right, from the end of the line." "Don't you see," said Lou, "it will be so nice. You'll wear everything once before you wear something twice." And with everything in queues in his closet and shelf, Jack started to feel quite sure of himself, all thanks to Lou and his wonderful queue.
So that paints a picture of these two abstract data structures. But if we really were to dive underneath the hood, we could implement them in a number of different ways. But we really, I think, need some building blocks via which we could solve problems like those. And we'll see today, too, some others as well. So let's